I'm a PhD student from Technion, Israel Institute of Technology. Today I'm going to talk about CBIM, object-level cloud collaboration platform for supporting a cross-domain, asynchronous design. So this study focuses on BIM or cross-domain collaboration in the design phase. Or cross-domain here means like multidisciplinary people involved in the project, like architects, structure engineers, MEP engineers, and so on. We are going to change the current file-based approach to an object-based approach to enable the cloud collaboration by compiling BIM models into graphs, link BIM graphs together, and apply intelligent applications on the linked graphs. So next, I will play a video, and then I will introduce like a tool how to generate the graph. Let's go. Building design involves many roles: architects, engineers, project managers, and so on. Currently, they use a file-based approach to exchange their designs. A typical project starts with the architectural design. The architect exports the model from software into IFC files and sends to engineers. Engineers reference this model for creating their own work in parallel. Afterwards, all models are fed into another software for clash detection. Users need to manually resolve the clashes before the next stage. The file-based approach has many problems. It is a sequential design. Users need to manually identify and resolve clashes. They also need to manage file versions on their own. We are imagining a future that embraces BIM cloud collaboration. You simply send the link, and everyone can edit the project from different devices simultaneously. But in BIM, the problem is more complicated. BIM incorporates many professional tools across disciplines and platforms. All of them use their own models instead of a single, holistic one. As such, the BIM collaboration platform must find a way to host the multidisciplinary data on the cloud and properly link the heterogeneous data at the object level. What will happen if they change their models? The system could monitor the change from one software and notify relevant users if their work is affected, like to provide geometry reference, or even offer intelligent suggestions to automatically resolve inconsistencies. Here we propose CBIM. User design in local software and use the CBIM connector to send the model to the cloud server, where it is represented as a graph. Same process for other discipline tools. Next, semantic enrichment algorithms generate inter-domain object relationships to link multidisciplinary graphs together. Those relationships could be design intent constraints, like the radiator could be attached to the wall, and the structure wall could be wrapped by the architecture wall with a corresponding relationship. After that, the mechanism monitors the change from any tool and computes suggestions to maintain consistency across models. CBIM compiles models as graphs and link objects together to enable intelligent applications. Let me show you our prototype. Here is an example. This project has an architecture model and a structure one. They are placed in two independent BIM software, both connected to the CBIM server. Now the architect moves the west wall to enlarge the room. Next, the architect uploads the change to the CBIM server through the CBIM Revit connector. In the cloud, the CBIM server receives the modification from the architecture software. This triggers the consistent maintenance mechanism to evaluate constraint relationships. The server detects violated constraints and attempts to compute propagation commands to resolve them. Consequently, within the structure software, the CBIM connector pops out the window, asking engineers permission to modify the model. If permission is granted, CBIM adjusts the beam and the columns automatically. If the change cannot be propagated automatically, as in the case of the bottom slab in this example, CBIM provides a geometry reference to support the design. Later on, the engineer pushes the updated design to the CBIM server. The server, in return, evaluates all constraint relationships once again and finds everything is consistent. A round of maintenance is completed. CBIM provides an object-based approach to enable BIM intelligent applications, such as automatic consistency maintenance we demonstrated in this video. This new way can enhance our cross-domain collaboration and improve working efficiency. So let's talk about one tool inside the CBIM platform. It's how we generate the BIM graphs from Revit. So in our domain, we do have some few tools which can generate BIM graphs from models. Like most of them use IFC files. And during the conversion process, most of them will abandon a lot of information like the geometry. But in our case, we want this graph generation process to happen inside BIM design software directly, like inside Revit. We hope we can keep as rich information as possible, especially the geometry, so it can enable the later machine learning algorithms that we use. Therefore, the CBIM Revit compiler can just read the model in Revit and compile it into a graph-based core extension database. In the core graph layer, it contains BIM objects and object relationships, like the window, the wall, the floor, and the wall hosts the window, the host relationship. And in the extension layer, any data which is not suitable to be represented as a graph will be stored here. In this case, the geometry file will be stored in the extension layer. So we follow the linked building data community ontologies to standardize the graph. For objects and relationships, we use BOT and BPO ontology. And for geometries, we use fog ontology. As you can see, like the virtual link here, so it's actually the address of the file, and we store this attribute inside the corresponding node. When you retrieve on the graph, you can know where the geometry it is. And for attributes, we didn't find suitable ontologies. If you have, please let me know. And then we just keep the Revit attribute name. I think people can understand it. We compile this graph in RDF format, so it can enable all the semantic web techniques. And all this data, all this code is available on GitHub. You can just go there, everything's already set up. So if you want to use a compiler, you follow the two-step procedures. Like you first load the Dynamo file inside the Revit, like in the Dynamo player. You just click the black button, and then it will generate some temporary files. Then you run the Python file. It will compile all the temporary files into a turtle file, the BIM knowledge graph. And we tested our approach on Revit 2022 and 2023, it works. And we tested it on some small and middle-sized projects, it works. But we need to point out, so like if we run really big projects, maybe this program will crash because like it reads all the information into the memory, and when it reaches the limitation of the memory, then the program might crash. And we tested on architectural apartments design. So in summary, we propose an object-based cloud approach to enhance our cross-domain collaboration. We call it CBIM. And we also develop a graph compiler which can export Revit models into BIM knowledge graph. And this code is open at GitHub. You can find all those information from the following two papers. One is like the conference paper in EC3, and another paper is already accepted by Automation Construction. So thank you very much. If you're interested in our work, please scan our code or LinkedIn. And this research from the cloud-based building information modeling project, which we received funding from European Union Horizon 2020 Marie Curie grant. Thank you.